Okay, we're going to dive a little bit deeper into limits today, dealing with some right and left hand limits and kind of a limit to memorize. But first of all, let's just review a little bit more with limits. I want to start by just, the first thing we should always try is just plugging the number in. Let me go to maybe the second one because it looks easy. If I plug in 4 times 4 is 16, minus 3 is 13. Let me just make a little note of that. This is 13. If I plug 4 into the next one, 3 times 4 minus 1 is 11. And 13 multiplied by 11 is 143. Easy enough. That's the limit. It's just the y value we're approaching. Let me go down a couple more. Let me go down to the bottom one here, because it looks like I could just plug 2 in. 5 multiplied by 2 cubed, so 5 times 8. Easy enough. It's just 40. Let's go up here. Try and just plug 2 in. 2 multiplied by 4 is 8, minus 6 is 2. And then this last one, we plug 2 in. 5 times 8 is 40. Divided by 4 is 10. And I just did that because it just looked like it was going to be pretty darn easy to do. Now, let me go to these ones that maybe look a little harder. Okay? If I plug in negative 1, I get 1 minus 3. So 1 minus 3 is negative 2, plus 2 is 0, and negative 1 plus 1 is 0. What that tells me is I should try and factor the top. So let's do that. Two things have to add up to 3 and multiply to 2. How about x plus 2 and x plus 1? Okay. Let me just kind of ignore this. Well, now you see that x plus 1 will divide out this x plus 1, and all I'm left with is x plus 2. So now try and plug negative 1 in with this factored version. Negative 1 plus 2 is positive 1. That's our limit. Okay, so there must have been a hole in that graph. Alright, let's try this one. 2 times 0 is 0, minus 0 divided by 0. So 0 divided by 0 again. Can't divide by 0. So let's try and do a little factoring. Well, if I took an x out of absolutely everything, I don't have a lot of room, so let me just do it this way. Let's factor this x out, and this x out. Now let's try and plug in 0. So 0 minus 6 is negative 6, divided by 3 is negative 2. Now you may think, well, why did you factor here? You didn't factor over here. Well, because if I plugged in 2, I got a nice number. I didn't need to do anything. It's when I get 0 divided by 0 that it clues me in. I've got more work to do. 0 divided by 0 clues me in. Whenever you get a 0 divided by a 0, that's called an indeterminate form. So you don't write undefined. You need to check factoring. I'm just going to put you need to do more. Okay, it's not enough to say it doesn't exist or it's an asymptote. You're going to need to do more because there's probably a hole in the graph. Okay, quick review of our definition from yesterday, and again, let's just think about limits. It's got to approach one real number from both sides of C. So I want you to think about this. As we approach 0, 1 over x, here we're approaching negative infinity. On the other side, we're approaching positive infinity. This limit does not exist. Now let's look at this one. 1 over x squared is spiking towards infinity, spiking towards infinity. Now, some textbooks will say, well, all right, it's infinity. At least it's infinity on both sides. Now, that's a lot different than this one, which was negative on one side and positive on the other. And yet, it's always troubling when people say, well, is that really approaching one real number? Couldn't you also say it does not exist since it's approaching infinity? You could. And actually, either one of these answers is acceptable. Next, 6x minus 7x squared over x. Well, plug in 0. 0 minus 0 over 0. It's kind of like that one we just talked about, where we must have something happening here that we could just plug in some numbers and do some simplifying. Or, I'm sorry, do some factoring. So again, in this interest of space, let me factor an x out of every term. I've got 6 minus 7x, so 7 times 0 over 1 is just 6. Now, talking about, sometimes we like to do a little bit more with limits where we actually define it on each side. We call those right and left-hand limits. Okay, left-hand limits come from the negative side, right-hand limits come from the positive side. They're denoted this way. You see, this says we got a function f of x, we're approaching 0 from the negative side. So as we approach 0 from the negative side, what y value are we approaching? Well, we're approaching a y value of 3. Please note, it does not matter that that's not what the function is defined at. Limits are what we're approaching. We're approaching 3. Well, this one says we're approaching 0 from the positive side. So we come back over and we start working our way towards 0 from the positive side. And again, we're approaching a y value of 3. So the limit as x approaches 0, well, we're approaching 3 from both sides. And there is a hole in the graph here, but that doesn't matter. It's what we're approaching. Okay. Next, approaching 2 from the negative side. So, from the negative side, we're approaching 2. Looks like we're approaching a y value of 5. From the positive side, looks like we're just approaching 3. So now, remembering that a limit has to be the same on both sides, approaching one number on one side and another on the other side, so the limit at 2 does not exist. Anytime we're approaching a different number on each side, the limit won't exist. So we could go out here to 4, and again the limit would not exist because it's approaching a different y value on either side of that x coordinate. Finally, a limit that at this point you may have to memorize is the limit as x approaches 0 of sine x over x. And I did include the picture here for you so you could look at it. This is sine x over x, and you can see, I think, that it is approaching 1. And that is its limit. And actually, as long as the coefficients are the same, for instance, you had sine of 2x over 2x, it'll always be 1. Okay. So as long as the coefficients are the same. Now the reason this is one to memorize is it comes up a lot and it's very, very useful. And of course, if you plug in 0, you get 0 over 0. But there's no factoring you can do with this. It's not like the ones we did earlier in this video. There's nothing you can do. So this is one you kind of need to know. And if you're wondering, well, why does that work out that way? Well, here's the graph of sine x and x separate. And I just want you to notice that right around 0, so right in here, notice how similar those two functions are. They're almost the same. And remember that if you take something and divide it by itself, you get 1. Well, sine x and x aren't the same, but they're really close. And remember, a limit is what you're approaching. So near 0, sine x and x are approaching the same exact thing, and that's why it's approaching 1, because they look so much alike at 0. So as I said, as long as the coefficients are the same, you can just say it's 1. Well, what if they're not? Well, the simple answer is you make them the same. You see this one right here, we've got sine of 2x over x. Well, I want that to be a 2. So I'm just going to make it a 2. Now, of course, you don't get to just multiply the bottom by 2 unless you also do the top by 2. But look how easy this is. This thing in the brackets is just 1. Okay? And 2 times 1 is 2. And that's it. That's all you need to do. Okay? Now, next you see this tangent of x over x, and you think, well, how does this apply? Well, remember, tangent can be written as sine over cosine. And over x, I can write that as 1 over x. Well, then I could just, multiplication works straight across. What if I rewrote this as the sine of x over x multiplied by 1 over cosine of x? And now if I plug in 0, again to find the limit, this thing right here is 1, and this thing right here, well, cosine of 0 is 1, so this is 1. So it just becomes 1 multiplied by 1, which is 1.